Okay, so it is 5, 7. I'm getting the diagram a little bit wrong here, but it's okay for the level of detail that we're going for. So Robert Millikan is the guy who figured out the charge to mass ratio of the electron. And I'm mentioning this because of the problems we're not doing in 17C, which is where we talked about equilibrium. So yesterday we took charges and we figured out the forces between them, the magnitude of the forces between them. We figured out, we were able to figure out based on how far apart they were and whether the charges were similar or oppositely charged, whether they had attractive or repulsive forces, and what the magnitude of those charges was. Great. Well, one application of that is finding a point where the charges are in equilibrium, where everything is balanced. And if it's in equilibrium, then there's no net force. So in essence, finding the point where the forces cancel one another out. So what Millikan did, and this was really fairly brilliant, is he took oil. I'm going to put oil in there. And he used what's called an atomizer bulb, which is, if you've ever seen a squeeze bulb, anything, that's an atomizer. It makes a fine mist of something. And he sprayed a bunch of oil droplets into a container, and like I said, I'm getting the diagram a little bit wrong, but it's okay. There was a very narrow opening in the top plate. So oil droplets could only pass through about 1 drop at a time. Well, the kicker is that this whole system was hooked up to a source of current, and once those oil droplets were midair, he was able to, starting off, that's right. Starting off, the top plate was negatively charged. So as the oil droplets passed through, they picked up a negative charge, just like you could pick up negative charges here. And they dropped through, so then they're suspended in air, and I'll have to make them a little bit darker, or a little bit larger maybe. That would work. So they're suspended in air, they're negatively charged, and then he would reverse the charges. Well, that drop is negatively charged. Starting out, it's being powerfully attracted to the positively charged bottom plate. Well, once he flips the charges, once he reverses the polarity of the system, now it gets attracted upward. What he would do would be to vary the electrical field until those charges hung suspended in midair. So gravity was pulling them down. Force of gravity was pulling them down. Once the top plate was positively charged, electrical force was pulling them up. When he could suspend them at the point where those charges were balanced, the equilibrium position, he was able to figure out the ratio of charge to mass. It's pretty, like I said, it's pretty brilliant, and it's relatively simple. I mean, you could basically mock this up. We could do it here with pie pans and hole punches and 9-volt batteries. It's not overly complicated, but beautiful in its simplicity. That's an example of equilibrium forces. We've got balanced charges. What we're talking about in 17C, which we're not going to calculate, it's that. We can find multiple point charges and get them to a point where, how far would they have to be apart in order to be perfectly balanced, to not be moving. So it's just basically playing teeter-totter with a bunch of point charges. We're not going to do the calculations, but that's what it is. Similar to Millikan's, except instead of using gravity to balance out electrical force, we're using multiple point charges to balance out electrical force. So this is about all we're going to do with electrical fields. They exist. You know that electrical force is a field force versus a contact force. Just like gravity, you don't have to be in contact with the electrical field for it to exert a force on you. You demonstrated that by charging up a bunch of objects and moving stuff that was not in contact. The magnitude is given in electrical field strength. And it's all about the charge per unit distance. So it's how much force is being generated and at what distance. The farther out you get from an object that's generating an electrical field, the weaker the field. Does this sound like another field force you're familiar with? Gravity. Once you escape, there's a point where you escape the zone of influence of the Earth, and the field is no longer exerting a force on you, then you've escaped the field. Same thing is true of electrical force. So Q is always magnitude of charge, R is always distance between the charge and the point being considered, and we're not going to do any of these calculations. Okay. If electrical force exists, and force is related to energy, in that energy is the ability to do work, which is force exerted over a distance, a charge can actually do work on a particle. And you saw that. You saw things moved by electrical force. A force was being exerted on them, and they moved some distance. So we have electrical potential energy, PE, it's another PEE. It's equal to the charge times the field strength, which was what we didn't calculate in the last problem, and we're not going to calculate this either, times how far away you are from the point. Now, there's all kinds of stuff with the direction of the field. There are all kinds of rules for it. You will do all of them if you are going on an electrical stuff. We will do none of them here. We will not do the right-hand rule. I can never remember this, but the right-hand rule involves the direction of field with moving current. And if you take your right hand and you wrap it around with your thumb pointing in the direction of the current, your fingers go in the direction of the field.
Oh boy.
Yeah. All the problems that you do with electrical field and electrical energy assume that the field is uniform. That depends on all sorts of factors that we're not going to talk about. You can imagine a uniform field because gravity is a uniform field. So there is no more or less gravity here than there is over there, than there is in Boise, Idaho, than there is in, outer Nepal. Okay, the field of gravity is uniform based on distance from the gravitational source. Okay, because the charge dictates the strength of the field, if you've got charges that have different magnitudes and they're really close together, you will get a field that is not uniform. So if we extend that, if we go back to the gravitational analogy, if we think about, do you know what twin stars are? They're just what they sound like. They're two suns that are linked in this sort of weird dance, and they orbit one another. They're twins. If they're different sizes, you would have an ununiform gravitational field somewhere in between them. You would have fields that are different strengths. In that case, we would have to use the magnitude of the field from each of them. We have the same issue with electrical fields. As long as you've got a single point charge, the field around it is going to be uniform. If you have two charges that are different magnitudes, you're going to have a field that varies. So, potential difference. You know what potential energy is. There is such a thing as electrical potential energy because there is the potential for the force exerted by a field to do work on an object. Just like with gravitational potential energy, there is the potential for the force of gravity to do work on an object. However, the mass of the Earth is constant. The mass of the Earth is not constantly changing. So the gravitational field is constant and consistent and uniform. The minute the charge changes, the field changes, and the field strength changes, and that means the potential energy changes. Does that sound like a recipe for a nightmare to you? Yes! Yes, it does, and it is. We don't use electrical potential energy much for that. We're not going to use it at all, but even as you go on, it's of a little bit less usefulness because of that fact that the field changes every time the charge does. What we usually use is the ratio of change in potential energy to charge. V. That make you think of anything you've heard of with electricity? Volts. So this is where we start to get to something that you will have heard of. what we typically use is delta V, or the change in electrical potential energy. Oh, capacitance. It looks like a weird word. It's one that every time I look at it, I have to think about how to pronounce it. A capacitor stores charge. So it literally stacks up electrons, charge carriers, we should say, on one side of some kind of insulator so that you have two charged objects.
So it's like a battery.
Be careful with that. It stores charge. Batteries do something a little different. They reshuffle charge carriers. But yeah, it stores charge momentarily within a circuit. So it's not the source of charge, which is the battery is actually a source of potential difference. But a capacitor stores charge. The earth and sky themselves in the moment before a lightning strike are acting like a big capacitor. Because you've got a bunch of charges on one side and a bunch of opposite charges on the other. And there's a moment of storage where there's a big difference in charge. The insulating material in the middle is air, which is actually a pretty good insulator. When that capacitor is discharged, what's the thing that happens? What discharges that sort of natural giant capacitor? Lightning. The spark, the jump, that is the discharging of this sort of, storm capacitor. So the oldest type is what's called a parallel plate capacitor. And this is literally two plates, just what it sounds like. Wire coming in, wire going out. You build up charge on one plate. You end up with a deficit of charge on the other plate. You store that charge until it builds to a certain point when it can no longer stand, when the attractive force between the two plates overcomes the insulation. We have kaboom. The capacitor discharges. The charge flows in the system again. Capacitors are actually the basis of, who here has intermittent windshield wipers? Okay. Those are, things like those intermittent things are based on different capacitors in a system where the system builds up charge, discharges, the windshield wipers go. Builds up charge, discharges, the windshield wipers go. So the low setting, where it only goes every so often, builds up a smaller amount of charge. The higher settings are able to build up do I have that backwards? Low amount of charge before it discharges, it's going to discharge more frequently. Right. So the is going to have a lower amount of charge it can store before it discharges. The very slow setting, so the one that maybe takes a minute in between swipes, is going to build more charge before it has to discharge. There's somewhere in there are multiple capacitors. Now those are no longer parallel plate capacitors. They're a different kind of capacitor. Well, might they be parallel plate? Probably not. They're probably a little circular, cylindrical capacitor. But yeah, when you move the indicator, you're changing what the circuit is connecting to. You're changing which capacitor it's embracing. On full speed, when they're just going, that's just a regular circuit where they're just continually swiping. And the speed control from slow to high, that one I don't know, it's beyond me. But I know that the intermittent settings are all capacitive. So, okay, so when we look at capacitance, it's a ratio of the net charge on each plate to that potential difference. So the difference in electrical potential of the separated charges. Who here has been told, turn it off, count to 30, turn it back on? Why do you count to 30? Because the capacitors in the system will hold charge even after the circuit has been disconnected from a power source. And so what you're really waiting for is the capacitors in the system to discharge. Now, the kind of capacitors that we'll use in circuits are really tiny. They don't hold a whole lot of charge. You're not going to get hurt if they discharge against your finger. There are larger systems that have big capacitors, And I'm trying to remember what the example was. This was actually in a physics class at YSU, and somebody was talking about circuits, and they had some older piece of equipment. It had been hooked up to a source of current. It had been disconnected for like a couple days. Had a big capacitor in it. Now, nobody died, but the person who took the system apart got a really good tickle. And the takeaway message was, make sure the whole system is discharged. And there's a methodology for doing that. I don't remember what it is. But capacitors can hold charge even after they're disconnected, which is why we typically, when we turn something off, we count to 30 before we turn it back on. This is movement of charge through a medium. And this is the thing that we teach you in chemistry, we teach you in physical science. Current is just the movement of charge carriers. There we talk about electrons, because electricity is just the movement of electrons. But current is that movement. And it's the rate at which the charge moves. So it's charge per area per time. And we think about this usually in terms of cross sections. So if we've got this pipe, so to speak, and we have charge carriers moving through it, we look at a single cross section of that, and we look at the area of that cross section and how many charge carriers move through it in a unit of time. That's current. Now, let's talk about units. Current is measured in amps, and 1 amp is 1 coulomb per second. We will actually do problem 19A, and then you've got 1 problem assigned. Okay, so we have a light bulb, and we're going to spend some time next week drawing circuits and drawing light bulbs, and you'll know why they're drawn like that. Current in a light bulb is 0.835 amps. How long does it take for a charge of 1.67 coulombs to pass a given point in that wire? So we're essentially saying, one single point, how long does it take for a charge to pass that point? Well, what we know is that the current, I, is equal to the charge divided by time. So current times time, whoops, what am I doing? Solving for the wrong thing, that's what I'm doing. So delta T is delta Q over I. So we have 1.67 coulombs of charge. We have 0.835 amps. Raw answer. Okay, so yes, it does come out that cleanly. 2 seconds, and that's it. Number 1 on the same page is assigned. 1 simple problem, 3-part algebra. The part that most people find weird is that I is current. Why can't we use C? Because C is taken for charge. So I is current. That's it for today.